So far in maths, we've been working with equations of the form y is equal to f of x. So for example, something like y is equal to x squared, where y is a function of x, and we call these Cartesian equations. In this video, we're going to talk about a new type of equation called a parametric equation. So rather than a Cartesian, where you have one equation to describe a graph that is equal to y, parametrics have two equations. One of these equations is equal to y and the other one is equal to x, and both of these are a function of another variable which we normally call t. So for example, x could be equal to t plus 3 and y could be equal to 2t minus 1. So how do these work? So let's just remind ourselves how Cartesians work. So we input a value of x, so let's say x is equal to 2, and we plug this into this equation here, y is equal to x squared. So y is going to be equal to 2 squared, so y is equal to 4. So a coordinate on the graph is 2, 4, where x is 2 and y is 4. With parametrics, we don't input x, we instead input t. So for example, t is equal to 2. And what we do is we sub this t value into these two parametric equations in order to get out the values of x and y. So if we start with x here, x is going to be equal to t plus 3, so it's going to be equal to 2 plus 3. 2 plus 3 is 5, so x is equal to 5. And then if we use this parametric equation here, y is going to be equal to 2t minus 1, so 2 times 2 minus 1, 2 times 2 is 4, minus 1 is 3, so y is equal to 3. So a coordinate on this graph is 5, 3, where x is 5 and y is 3. Note that in parametrics, this t equal to 2, this input, doesn't actually appear in the final coordinate. Compare this to Cartesians, where the input x is equal to 2 is in the final coordinate. And then that's how parametric equations work. We input t values such as t is equal to 2 into these equations for x and y in order to get out coordinates like 5, 3. If we input more t values, so for example t is equal to 3, t is equal to 4 and t is equal to 5 into these two parametric equations here and do it in the same way that we did before, we get out the coordinates of 6, 5 for t is equal to 3, 7, 7 for t is equal to 4 and 8, 9 for t is equal to 5. If we plot these 4 points here, we get this graph here, and you can see these parametric equations here represent a straight line. Now I've chosen this quite simple example here where it just makes a straight line to show you how parametric equations work. But one of the useful things about parametric equations is that they can be used to make quite unusual and interesting graphs that Cartesian equations cannot produce. So for example, let's say that we have the two parametric equations, x is equal to t cos t and y is equal to t sin t. You get this graph here. I've made this using Desmos, and you can see this kind of really weird graph here. You'd never be able to make this using Cartesian equations, so this is one of the advantages of parametric equations. A very common exam question for them to ask is to convert a parametric equation to a Cartesian equation. So here's an example of this, where we're told about a curve that has the parametric equations x is equal to half t plus 2 and y is equal to t squared minus 5, and we need to find a Cartesian equation of this curve in the form y is equal to f of x. Okay, so the way that we're going to tackle this is we're firstly going to focus on the x parametric equation, and we're going to rearrange it to make t the subject. Okay, so if we look at this parametric equation, firstly we're going to move this plus 2 to the other side, so it becomes x minus 2 is equal to a half t, and then we're going to multiply both sides by 2 to get rid of this half here. So we get, if we multiply this side by 2, it'll be 2x minus 4 is equal to t. So we've made t the subject, and now we're going to look at the other parametric equation, so this y is equal to t squared minus 5. And what we're going to do, this t here, we're going to sub this out for this 2x minus 4. So therefore this parametric equation here is going to become y is equal to, and we've got t squared here, so rather than this t, we're going to have this 2x minus 4 and it's t squared, so it's going to be 2x minus 4 to the power of 2. and then we've got this minus 5 on the end here, and this here is in the form y is equal to f of x. We've got rid of the t terms in this equation, and we've got it in the Cartesian form. Now, you could go further than this. You're allowed to leave it in this form because this is in the form y is equal to f of x. You could go further with this and expand this bracket. So we have this squared here, so it's going to be 2x times 2x, which is 4x squared, and then 2x times minus 4, which is minus 8x, but this is going to be twice, so it's going to be minus 16x, and then minus 4 times minus 4, which is plus 16, and then we have this minus 5 on the end, and then 16 minus 5 is 11. So if you wanted to get it in the quadratic equation format, it's this down here in the form y is equal to f of x. Okay, so here's another example where we're told a curve has parametric equations x is equal to e to the power of t and y is equal to t squared plus 4, and we need to find a Cartesian equation again. So let's do the same method as before. So let's first focus on the x parametric equation. The x is equal to e to the power of t, and we need to make t the subject here. So what we're going to just do is take the natural log of both sides, so it becomes the natural log of x is equal to t, and we've made t the subject. And now what we're going to do is sub out this t here for this natural log of x. So therefore it becomes y is equal to, then rather than t squared, it's going to be the natural log of x squared, like this here, and then plus form. So therefore this is a Cartesian equation of the parametric equations in the form y is equal to f of x. So here's another question where we're told that a curve has parametric equations x is equal to the natural log of t minus 2 plus 3 and y is equal to 1 over t minus 2. And we're also told that t is bigger than 3. So what this is the domain for this curve. So that means that any values that don't fit into this domain, so when t is less than 3, we can't sub these in. So therefore, in order to sub in a value of t, it has to be bigger than 3. Okay, this is the domain. And for part A, this is the normal, find the Cartesian equation. Then for part B, we need to state the domain and range of f of x. F of x is this function that we find in part A. This is quite a common exam question that you like to ask, part B, but we'll start with part A because this is just the normal find a Cartesian equation. This domain here, we don't need to worry about this for part A, this only comes in for part B. So we're going to do the normal. So if we start with the parametric equation for x, so we're going to rearrange this in order to make t the subject. So this plus 3, first we're going to move this onto the other side, so it becomes x minus 3 is equal to the natural log of t minus 2. And then what we're going to do is we're going to make both sides powers to base e. And the reason we're going to do that is because this side here, remember, when you do e to the power of the natural log of something, this e and the natural log cancels out to just leave you with a. So therefore, if we make both sides powers to base e, so this side here will become e to the power of x minus 3, and if we do it on this side here, we'll get this effect up here, and this natural log will cancel out and just leave us with t minus 2, like this is. So we get that e to the power of x minus 3 is equal to t minus 2. Again, go back to the laws of logs video if you need a reminder of how that works. And normally, as I said, we normally rearrange in order to make t the subject here, so we'd put the minus 2 on this side here. However, you can actually see that for y, the denominator is this t minus 2 that we've made the subject here. So what we're just going to do is we're going to keep it like this, and we're going to sub out this t minus 2 for this e to the power of x minus 3, and we don't need to go for the bother of bringing the 2 onto this side. So therefore this y here, if we sub this out, it's going to be y is equal to 1 over, and then instead of t minus 2, it's going to be this e to the power of x minus 3. If you remember your laws of indices, if you have 1 over e to the power of something, like for example e to the power, let's call it e to the power of a, this is equal to e to the power of minus a. Remember, this is what a minus power means. It means it's 1 over, like this here, it has this 1 numerator. So therefore we can rewrite this here as e to the power of minus x minus 3. So I've added this minus here, which represents this 1 numerator. Then we can expand this bracket here so it becomes e to the power of 3 minus x, like this here. So y is equal to e to the power of 3 minus x. Okay, and then for part B, we need to state the domain and range of f of x. And as I said, this is quite a common exam question for them to ask to do with parametrics. So f of x is this function here that we figured out in part A. Now, we did a video kind of about 3 years ago now called functions. And in that video, we talked about what the domain and range are. But just to recap quickly, the domain is the x values that you can put into a function, and the range is the y values that you can get out of a function. And one thing that's really good about parametric equations is it's really easy to figure out what the domain and range are. So why is this? Okay, so the domain is the possible x values, and one thing that's really good is we have a parametric equation with x as the subject. Okay, so in order to figure out what the possible x values are, we just need to consider the range of values that this function here gives out for this t inequality here. So the domain, the x values, is the range of this function here given this inequality. And it's pretty much the same for the range. So the range is the possible y values. And you can see here that we have an equation with y as the subject. So therefore the possible y values are going to be the range of values that this function here, 1 over t minus 2, can give out for this inequality here where t is bigger than 3. Okay, so let's first consider the domain. So this is the range of values that this function here, the natural log of t minus 2 plus 3, can give out for this inequality here where t is bigger than 3. Now, for questions like this, I think it's best to zoom in as narrow as you can firstly, and then as you're going on, kind of zoom out. So what do I mean by that? So let's start with considering this t minus 2 here, okay? So as t has to be bigger than 3, that means that t minus 2 has to be bigger than 1. I've essentially just taken 2 from both of these sides here, okay? So now let's zoom out a bit, the natural log of t minus 2, okay? So as the smallest value that t minus 2 can have is 1, that means we're going to have the natural log of 1 here, which is 0. If we start to increase this number here, so if we start to increase t minus 2, so for example, let's say the natural log of 2, it doesn't matter that much, but if you put this into a calculator, it's equal to 0.69. If you keep increasing this number, so for example, the natural log of 3, this is equal to 1.09. The point being is that when you increase the value of t minus 2, the natural log keeps getting bigger. So that means the natural log of t minus 2 is going to be bigger than 0, with the smallest value being 0 here, when this t minus 2 is its smallest value of 1. Okay, now let's consider the natural log of t minus 2 plus 3. So I've just added 3 to both sides here, so this is going to be bigger than 3, like this here. And you can see that this is what x is equal to. X is equal to the natural log of t minus 2 plus 3. So therefore we can just sub out this here for x. So therefore it's going to be x is bigger than 3, and this here is the domain. X is bigger than 3. Okay, so now let's consider the range. So this is the possible y values, and this is going to be the range of values that the function 1 over t minus 2 gives out. So like I talked about before, let's kind of zoom in as much as possible and then zoom out as we go on. So let's first consider t minus 2, and this is the same as before. T minus 2 is bigger than 1. Okay, now let's consider 1 over t minus 2. Okay, so the smallest value that t minus 2 can have is 1, so this will be 1 over 1, which is equal to 1. As we start to increase this number, so as we start to increase t minus 2, so let's consider 2, it will be 1 over 2, like this here, so it'll be a half. As it starts to increase, it will then be 1 over 3, and then it'll be 1 over 4, and 1 over 5, etc. The point being, when this number gets bigger, the 1 over t minus 2 actually gets smaller, okay? So you can see that the biggest value that 1 over t minus 2 can have is 1 here. This is actually when t minus 2 is equal to 1. And then from here it gets smaller. So 1 over t minus 2 is less than 1. Now there's one other thing you need to consider with this inequality. 1 over t minus 2 will also always be bigger than 0. It won't be a negative number. The only way that this would be a negative number is if t minus 2 was negative. So if something like 1 over minus 1, for example, then it would be equal to minus 1. However, t minus 2 cannot be negative, so therefore this cannot be negative either. So therefore 1 over t minus 2, this is what y is equal to, so therefore we can just sub in y here. So y lies between 0 and 1, so this here is the range, okay? And that's the answer here. This here is the domain where x is bigger than 3, and this here is the range where y is between 0 and 1. If you have parametric equations involving trig functions, rather than doing a straight substitution like we've seen in this video, where we start with the x equation, we make t the subject, and then we sub this into the y equation, rather than doing that, we can instead use trig identities that we've learned in previous chapters in order to form a Cartesian equation. So here's an example of this, where we're told that a curve has parametric equations, x is equal to 2 plus cos t, and y is equal to minus 4 plus sin t. And for part A, we need to find a Cartesian equation of this curve. Now what's quite interesting about part A, it doesn't mention anything about getting it in the form y is equal to f of x. Now I told you at the beginning of the video that the definition of a Cartesian equation is getting it in this form y is equal to f of x, and I just said that definition for simplicity. That's not actually what a Cartesian equation is. A Cartesian equation is just an equation that's made up of y and x. It doesn't actually have to be in this form here, it just most commonly is in the form y is equal to f of x. It only needs to have x and y in it though, so we don't need to get it in this form. So if we look at these parametric equations, so we're going to start with this x one here, so x is equal to 2 plus cos t, and we're going to move this 2 onto the other side, so we get that x minus 2 is equal to cos t. And then if we look at the y parametric equation, if we move this minus 4 onto the other side, we get that y plus 4 is equal to sin t. So we've made cos t and sin t the subject here. And what's useful about this is we can use the trig identity that we learned back in year 1, that if you have sin squared of something, plus cos squared of something, it's always equivalent to 1. So in this case, sin squared of t plus cos squared of t is equivalent to 1. And what we can just do is sub in this sin t here and this cos t here. So this sin t here is y plus 4, so it's going to be y plus 4 squared, remember, and then it's going to be plus this cos t squared, so this x minus 2 squared like this here, and this is going to be equal to 1. And this here is a Cartesian equation because it's only made up of y and x terms, and you might recognize this as the equation of a circle. It might be easier if we write it the other way around like this here with the x term coming first. This here is the equation of a circle. So we found a Cartesian equation for this curve. Okay, and then for part B, we need to draw a sketch of this curve. So we need to draw a sketch of this circle here. So this is, we did a video on the equation of a circle back in year 1 of chapter 6. So go back to that if you need a reminder. But in case you need a refresher, so the equation of a circle is this here, where it's x minus a squared plus y minus b squared is equal to r squared, where the center of the circle is a, b, and the radius of the circle is r. Okay, so if we look at this equation of a circle here, we can see that the center is going to be 2 minus 4, and the radius is going to be the square root of this number here. So it's going to be the square root of 1, and the square root of 1 is just 1. So we need to draw a circle with center 2 minus 4 and radius 1. So this is going to look something like this here, where we have the center point 2 minus 4 and we have a radius of 1. So that's a sketch of the curve. Okay, so here's another example question where we're told about a curve that has parametric equations, x is equal to 3 sin t and y is equal to sin 2t. And we're also told about the domain of t, which is between minus pi over 2 and pi over 2. And for part A, we need to find a Cartesian equation of the curve in the form y is equal to f of x. Now, I've slightly adapted this question from an example in the textbook. I've changed some details about it, but I have adapted it from an example in the textbook, which I normally avoid doing. But I think this question is a very good example of using trigonometric identities in order to make Cartesian equations. So when we look at the two parametrics, the first thing that sticks out is this sin 2t here with the 2 inside the trig function. And when you have something like this is a sign that you need to use the double angle formula. Now, we did a video on the double angle formula back in year 2 of chapter 7, so go back to that if you need a reminder. But the double angle formula for sin 2t, it's equivalent to 2 sin t cos t. So what we can do is we can rewrite this y parametric equation here. We can rewrite it as y is equal to 2 sin t cos t. And what's useful about this is this sin t here, we have it in this x parametric equation. So what we can do, if we focus on this parametric equation here, if we divide both sides by 3, we get that 1 over 3x is equal to sin t, and therefore we can sub out this sin t here for 1 over 3x. So this can become y is equal to 2, and then instead of this sin t, it's 1 over 3x, and then this cos t, and then 2 times 1 over 3 is 2 over 3. So that means that y is equal to 2 over 3x cos t. Now this isn't a Cartesian equation, because even though we have y and x, we also have this t here, this cos t, so we need to get rid of this. And the way that we're going to do that is we have this equation here with sin t as the subject, and if you consider the trigonometric identity that sin squared t plus cos squared t is equivalent to 1, if you move this sin squared t to the other side, you get that 1 minus sin squared t is equivalent to cos squared t. So what we can do is we can sub out this sin t here for this 1 over 3x and get an equation that involves cos t. Okay, now for this we need sin squared t. So what we're going to do with this equation, we're going to square both sides. So this side here becomes sin squared t, and then this side here will become 1 over 3x to the power of 2. Therefore we can sub out this sin squared t here, so it becomes 1 minus, and then instead of sin squared t, it's this 1 over 3x to the power of 2, and this is equal to cos squared t. Now to sub out the this here, we need cos t, so what we're going to do, we're going to square root both sides here, so it becomes cos t is equal to the square root of 1 minus 1 over 3x to the power of 2. Just quickly, we don't need to worry about the plus or minus here, because in this domain between for t between minus pi over 2 and pi over 2, cos t cannot be negative, so we don't need to worry about this being a negative value. It's always going to be the positive one. So therefore we have this here is equal to cos t, and then we can sub out the cos t here for this, so we can write this as y is equal to 2 over 3x, and then the square root of 1 minus 1 over 3x squared, like this here. Now this here is of the form y is equal to f of x, and we've got rid of all of the t terms, so this is a Cartesian equation, so you can leave this as the final answer. If you wanted to go a bit further though, what you could say is that 1 over 3x to the power of 2 is 1 over 9x squared, like this here, and this 1 minus 1 over 9x squared, if you factorise out 1 over 9 from it, you get in this square root here, you get 1 over 9, and then if you factorise 1 over 9 out of 1, it becomes 9, so it's 1 over 9, 9 minus x squared, and then the square root of 1 over 9 is equal to 1 over 3, so you can bring this out of the square root, and then 2 over 3 multiplied by 1 over 3 is 2 over 9x, and then the square root of 9 minus x squared. So this is a bit of a simplified format of writing it. You don't have to go through this, as the question just asks you to get it in this format here though. And then for part B, we need to state the domain and range of f of x. And we talked about a question like this before. So remember, the domain is the possible x values and the range is the possible y values. And if we consider this in the context of the parametric equation, so if we start with this x1 here, so the domain, which is the possible x values, is just going to be the range of values that 3 sin t gives out. And then the range, which is the possible y values, is just going to be the range of values that sin of 2t gives out. Okay, so if we start with the domain, so this is the range of values that free sin t gives out. So let's start with sin t, and we need to consider this domain of t here between minus pi over 2 and pi over 2. So if we consider sin t, if we draw a sin graph between minus pi over 2 and pi over 2 like this here, you can see that the biggest value that sin can have is 1. This is when it's at pi over 2, and the smallest value that it can have is minus 1, and this is when it is at minus pi over 2. So therefore the range of sin t is the lowest value is minus 1 and the biggest value is 1. It can be equal to both of these values here. That's why we use these inequality signs, because t can be equal to minus pi over 2, and it can be equal to pi over 2 like this here. And then we need to consider free sin t, so we just multiply everything by 3 here. We get the free sin t is bigger than or equal to minus 3 but less than or equal to 3, and that's what x is equal to. So if we just sub out this free sin t for the x, we get that x is bigger than or equal to minus 3 but less than or equal to 3. So this is the domain. And then if we consider the range, so this is the possible y value, so therefore we're going to consider the range of values that sin of 2t gives out. Now remember that when you have a multiplier inside a trig function like this here, if you remember graph transformations, this squeezes the graph in the x direction by 2. So therefore, if you look at the graph y is equal to sin of 2x, it looks like this here, where it's the same as y is equal to sin x, but everything has been shrunk in this direction by 2 along the x-axis. Now you can see that the range of values that this gives out is the same. The biggest value is at 1 and the smallest value is at minus 1. So therefore the range of values of sin 2t, it's bigger than or equal to minus 1, but it's less than or equal to 1 like before. So therefore this sin 2t, if we just sub this out for y, we get that y is bigger than or equal to minus 1, but smaller than or equal to 1. So this here is the range and this here is the domain. Okay, we're going to go through some past exam questions in one moment, but there's one more thing I want to cover quickly that they like to ask, and that's to do with parametric equations and points of intersection. So here's a question that I've written that's to do with this. So we're told about a diagram that shows curve C, so this is this diagram here, and we're told this curve C has parametric equations. X is equal to t squared minus 2 and y is equal to t squared minus t. And for part A, we need to find the coordinates of the points of intersection with the y-axis. So if we look at the diagram, the y-axis is here, so as it's where the curves intersect in the y-axis, it's going to be these 2 points here. Okay, so we need to find what these 2 points are. Okay, now as it's intersecting with the y-axis, this is going to be where x is equal to 0. So what we're going to do here is we're going to consider this parametric equation where x is equal to 0. So this is going to be 0 is equal to t squared minus 2. If we move this minus 2 to the other side, we get that t squared is equal to 2, and then if we square root both sides, we get that t is equal to plus or minus root 2. Okay, so what this means is that this point of intersection with the y-axis, these 2 points of intersection, occur when t is equal to plus or minus root 2. But we don't need the values of t, we need the values of y for when this happens in order to get the coordinates. So what we're going to do with these values of t, we're going to sub these in to the y parametric equation. Okay, so if we start with the positive root 2, so this is going to be y is equal to root 2 squared minus root 2. If we follow this equation here, root 2 squared is 2, so therefore y is going to be equal to 2 minus root 2. So therefore one of the points of intersection is 0 because the x coordinate is 0, and 2 minus root 2. And then if we sub in the t is equal to minus root 2, it's going to be y is equal to minus root 2 squared, and then it's minus t, so if it's minus root 2, it's going to be plus root 2 like this here, and then minus root 2 squared is 2. So therefore it's going to be y is equal to 2 plus root 2, so the other point of intersection with the y-axis is 0, 2 plus root 2. So these are the two y-intercepts. Okay, and then for part B, we need to find the coordinates for the points of intersection with the x-axis. So this is going to be these 2 points down here and as it intersects with the x-axis, this is going to be where y is equal to 0. So this is the exact same technique as before, but now we use this parametric equation and we set y to 0. So therefore it's going to be t squared minus t is equal to 0, and then if we factor out t, we get that t minus 1 is equal to 0. So that means that either t is equal to 0 or t minus 1 is equal to 0. So that means that t is equal to 0 or 1 is equal to 0, like this here. So if we sub in the t is equal to 0 into this x parametric equation here, we get that x is equal to 0 squared minus 2, which is just going to be minus 2. So x is equal to minus 2. So therefore, one of the points of intersection with the x-axis is minus 2, 0. Then the other one is going to be where t is equal to 1. So it's going to be x is equal to 1 squared minus 1. 1 squared minus 1 is just minus 1. So therefore, the other x-intercept is going to be minus 1, 0. Okay, and then for part C, we're told that the line y is equal to 2x minus 2 intersects curve C twice. Okay, so what this is going to look like, we're going to have a line y is equal to 2x minus 2. So this is just going to look something like this here, and it's going to intersect this curve here twice. For example, one here, and then for example, if we continued this curve like this, it's going to intersect it one more up here as well. And we need to find these 2 points of intersection. Okay, now the easiest way to do this is if we look at this equation here, y is equal to 2x minus 2. What we're just going to do is sub in the parametric equations into this line. So for y here, we're going to sub in the t squared minus t for the y parametric equation, and for the x, we're going to sub in this t squared minus 2 for the x parametric equation. So it's going to look something like this here, where instead of y, it's going to be t squared minus 2, and this is equal to 2, and then instead of x here, it's now going to be this t squared minus 2, and then we've got this minus 2 on the end here like this. And what we're going to do is we're going to find the t values for this equation. Okay, so firstly, if we expand this bracket here, it's going to be 2t squared minus 4, then minus 4 minus 2 is equal to minus 6, and then what we're going to do, we're going to bring this stuff onto this side in order to make a quadratic equation. So it's going to be 2t squared minus this t squared, so it's going to be t squared, then this minus t is going to go on this side and become a plus t. So we've made this quadratic equation that t squared plus t minus 6 is equal to 0, so therefore we need to solve this in order to find the values of t. Easiest way of doing this is just by factorising, and we can factorise this into t plus 3, and t minus 2 is equal to 0. So therefore t is going to be equal to minus 3 and 2, so these are the t values for where these points of intersection occur. Now, of course, we don't need the t values, we need the x and y values to find these coordinates. So what we're going to do with these t values is we're going to sub them into these parametric equations in order to get the values of x and y out, okay? So if we start with minus 3, so if we consider x, this t squared minus 2 equation, it's going to be minus 3 squared minus 2 if we sub it in like this, and then minus 3 squared is 9, and 9 minus 2 is 7, and then y is equal to t squared minus t, so if we sub in t is equal to minus 3, it's going to be minus 3 squared, and then minus 3, so it's going to be plus 3, then minus 3 squared is 9, plus 3 is 12, so therefore one of the coordinates when t is equal to minus 3 is going to be 7, 12, then the other one is going to be when t is equal to 2, so that means x is going to be equal to 2 squared minus 2, like this here. 2 squared is 4, 2 minus 2 is 2, and then y is going to be equal to this t squared minus t, so it's going to be 2 squared minus 2, which is also equal to 2, so therefore the other coordinate is 2, 2. So this is these are the 2 points of intersection with the line y is equal to 2x minus 2. Okay, so now we're going to move on to some past exam questions. So here's an example of one. So we're told about a curve C that has the parametric equations x is equal to 2t minus 1 and y is equal to 4t minus 7 plus 3 over t. And we need to show a Cartesian equation of this curve can be written in this format here, and we need to find what A and B are. Now the way we're going to do this is the way that we normally approach parametric equations, converting them to Cartesians. We're going to focus on the x parametric equation and make t the subject, and then we're going to sub this t value into the y parametric equation. So if we start with the x parametric equation, if we move this minus 1 to the other side, we get x plus 1 is equal to 2t, and then divide both sides by 2, so we get that x plus 1 over 2 is equal to t. So if we sub this into the y parametric equation here and here, we get that y is equal to 4, and then it's going to be t, so it's going to be this x plus 1 over 2, because that's what we've subbed in. Then minus 7 plus this 3 over t. Now, another way we can write this is 3 multiplied by 1 over t. So it's going to be 3 multiplied by 1 over this fraction here. Remember, when you do 1 divided by a fraction, it flips this fraction here. So another way to write this is 3 multiplied by this flipped fraction 2 over x plus 1, like this here. And we need to get it into this format here. So firstly, let's expand the bracket. So we've got 4 multiplied by this here. So this 2 denominator will cancel out with this 4 here to leave us with a 2 at the front here. So it's going to be 2 times x plus 1. So it's going to be 2x plus 2. Then we've got the minus 7, and then we've got plus 3 times this. So 3 times 2 is 6, so it's going to be 6 over x plus 1, and then plus 2 minus 7 is equal to minus 5. So we have y is equal to 2x minus 5 plus 6 over x plus 1. Now we need to get it into this format here, this fraction, with the denominator being x plus 1. So the way that we're going to do this, we have this denominator here, so that's fine. We need to focus on this 2x minus 5, and what we're going to do is this 2x minus 5, we're going to multiply it by x plus 1 over x plus 1. Remember, x plus 1 over x plus 1 is the equivalent to 1, so we're not changing the value of it. And if we do this, it's going to be 2x minus 5 times x plus 1 over x plus 1, and then plus this 6 over x plus 1. Okay, so if we simplify this, so 2x multiplied by x is 2x squared, minus 5 multiplied by x is minus 5x, 2x multiplied by 1 is 2x, and minus 5 multiplied by 1 is minus 5. And I've also moved, because the denominators are the same here, we can add these two fractions. So I've moved this 6 into this fraction here, so it's like this here. And we can do some simplifying. Minus 5x plus 2x is minus 3x, and minus 5 plus 6 is equal to plus 1. So we have it in this format here, which is what's required, where a is minus 3 and b is 1. Really quick, the question doesn't actually ask about this, but you see that the domain changes. So the domain before is any number, but t can't be equal to 0, and the domain changes when it's x, where x can be any number, but it can't be equal to minus 1. The reason it does this is you just plug this t is not equal, cannot be equal to 0 into the x parametric equation like this here, so it becomes 2, 0, minus 1, which is equal to minus 1. So that's kind of where this x can't be equal to minus 1 comes in. We've converted it from t to x. Okay, so here's another exam question where we're told that a curve C has parametric equations x is equal to 3 plus 2 sin t and y is equal to 4 plus 2 cos of 2t. We're also given this domain here. T has to be between 0 and 2 pi. And for part A, we need to show that all the points on C can satisfy this equation here, so we essentially need to convert it to this Cartesian. Now, the way that we're going to do this is, if you look at the y parametric, we have this cos 2t with the 2 inside the trig function. So this is a clue that we're going to use the double angle formula. And for cos 2t, remember you have two of them. You have the sin version and the cos version for the double angle formula. As we have sin t in this x parametric equation, it makes sense to use the sin version. So therefore we can sub out the sin t when we have it for an x term, and therefore we can make the Cartesian. So for cos 2t, the double angle formula for sin is 1 minus 2 sin squared t. So if we sub this into the y parametric equation for cos 2t, we get y is equal to 4 plus 2, and then instead of cos 2t here, we have the 1 minus 2 sin squared t, like this here. And then we're going to expand this bracket because we have this 2 here. So 2 times 1 is 2, and 2 times 2 sin squared t is equal to minus 4 sin squared t, like this here. And then 4 plus 2 is 6. So y is equal to 6 minus 4 sin squared t. Okay, so what we're going to do now is we're going to rearrange this x parametric equation in order to make sin t the subject. So if we move this 3 here onto this side, so it becomes x minus 3 is equal to 2 sin t, and then if we divide both sides by 2, we get that x minus 3 over 2 is equal to sin t. We need it to be sin t squared. So therefore, if we square both sides, we get that sin t squared is equal to this x minus 3 over 2, and all of this to the power of 2. So if we sub this in here, we get that y is equal to 6 minus 4, and then instead of this sin squared t, we have this x minus 3 over 2 to the power of 2. Now we need to write it in this format here. The way that we're going to do this is we have this power of 2 and we have this 2 in the denominator. 2 squared is 4, so we can write it as this here with this x minus 3 being squared here, and then we've already squared the denominator to 4, and then 4 times 4, these will cancel out, the denominator will cancel out to leave us with y is equal to 6 minus, and then this x minus 3 to the power of 2, which is what's required. Okay, and then for part B, we need to sketch the curve C, and then we also need to explain why C does not include all points of y is equal to 6 minus x minus 3 to the power of 2, where x is all real numbers. Now we'll come back to this second part in a moment. Let's first focus on sketching this curve C that has this equation here, this y is equal to 6 minus x minus 3 to the power of 2, and hopefully you can realise this is a quadratic, and we know how to sketch quadratics back in year 1 of chapter 2. And one of the things hopefully you can notice as well, that this is in the completed square format. So just a reminder, a completed square format is this here, where y is equal to x plus p to the power of 2 plus q. And one of the things that's nice about the completed square format, you might need to go back to the videos that we did in year 1 chapter 2 on quadratics. One of the things that's nice about the completed square format is it's really easy to tell what the turning point is of a quadratic. The turning point is going to be minus p q, where p is this number here inside the bracket to the power of 2, and q is this number here. So if we consider our equation here, p is this minus 3 here, and q is this 6 here. So therefore the turning point here is going to be minus p. Now p here is minus 3, so minus p is going to be minus 3, so it's going to be positive 3, and q is 6. Therefore the turning point here is going to be 3, 6. Now you might be tempted at this point to just draw the quadratic. It's going to be a negative parabola because if you think about it, we have this minus here, so if we expanded this bracket and times it by the minus at the front, the coefficient of x squared will be minus, it would be minus x squared, so it would be a negative parabola. So it would look something like, if we draw a y and an x-axis, it will look something like this here, with this being this turning point 3, 6. However, there's something really important with this question you need to consider, and it's the fact that it's made from parametric equations. And we're going to consider what the domain is for x here. So remember, to find the domain, which is the possible x values, remember that's what the domain is, we're going to consider the range of values that 3 plus 2 sin t gives out in this interval here between 0 and 2 pi for t. So let's look at this. So let's first consider this sin t here. So this is a graph of sin t between 0 and 2 pi, which is the domain here, and you can see that the biggest value in this domain that the sin graph can have is 1, which is here, and the smallest number that it can have is minus 1, which is here. It can be equal to both of these values as well, because this one happens at pi over 2, which t can equal, and this minus 1 happens at 3 pi over 2, so it can be equal to both these values as well. We have 2 sin t here, so if we multiply everything by 2, it's going to be between minus 2 and 2, and then this is 3 plus 2 sin t, so we're going to add 3 to everything, so it's going to be that 3 plus 2 sin t is bigger than 1 but smaller than 5. So if we sub out this 3 plus 2 sin t for this x, we get that the possible x values for this curve here, C, is between 1 and 5. And that's really important because when we're sketching this curve here, we can only do it between, say, x is equal to 1 and x is equal to 5. We can't include these sections here because they're not in the domain between 1 and 5. Okay, so now we know that we're going to be drawing a quadratic with a turning point 3, 6, and with the domain between the x values between 1 and 5. So it's going to look something like this here. Now, in order to get all the marks for this question, one of the things that the mark scheme talks about is it also wants you to find what they call the endpoints here. Now, we know that this is going to be where x is equal to 1 and x is equal to 5 because this is the ends of the domains, but it wants you to find the y coordinates as well, which I think is a tiny bit harsh because it doesn't actually say that in the question that you need to give that. So I think it's possible you might overlook that and you might lose marks because of that according to the mark scheme, but you need to find these points. They're very easy to find though because we know that there is when x is equal to 1 and x is equal to 5. So what we can just do is sub them into this equation here in order to get the y values out. So that's what I've done here. So this is where I've subbed in 1, so it's going to be y is equal to 6 minus, and then instead of x here it's 1 minus 3 squared like this here. 1 minus 3 is minus 2, so square that is 4, so 6 minus 4 is 2. So that means that this point here is going to be 1, 2, and then the other one is when we sub in x is equal to 5, which is going to look like this here. 5 minus 3 is 2, 2 squared is 4, 6 minus 4 is 2. So this is 5, 2, so this point here is 5, 2. And then that's how you get all of the marks. As I said, I think it's a bit harsh because it doesn't say that you need to give these endpoints. I guess the reason is because if you don't calculate the y values, you don't know if this curve is going to go under the x-axis like this in the domain. However, now that you know the y values are 2 and 2, you know that it will stay above the x-axis in this domain here. And then for the second part, just explain briefly why C does not include all the points of y is equal to this when x is all real numbers. We've kind of already answered this. Just write a statement where for this curve here, C, the domain is between 1 and 5, whereas here the domain is all real numbers. This graph here that it's describing here would be the same quadratic, but it would keep going all the way for all the real numbers. Okay, and then for part C, we're told that the line with equation x plus y is equal to k, where k is a constant, intersects C at two distinct points, and we need to state the range of values of k, writing our answer in set notation. So let's actually break down what's going on in this question, okay? So we have this line here. So what we're just going to do quickly is we're going to move x to this side, so therefore it becomes y is equal to minus x plus k, and we can see that this is a straight line. This is in the y is equal to mx plus c format, where the gradient is minus 1 and then k is the y-intercept for this line. Now we're told it intersects c at two distinct points, so that means this line here is going to look something like this, where it intersects c at two distinct points and it has a y-intercept of k. Now we need to state the range of values of k because of course this could also be up here, this line for example, and it still intersects it twice, or it could be like down here and it still intersects it twice. So we need to find the range of values of k for which it intersects the curve twice. And the way that we're going to do this is, so we've made y the subject here, and what we're going to do is we're going to sub out the y here for this minus x plus k because we're dealing with points of intersection, so we're going to substitute this minus x plus k into this here, so it becomes minus x plus k is equal to this 6 minus x minus 3 to the power of 2. Okay, now let's simplify this. So we have this x minus 3 to the power of 2, so if we expand this it's going to be x squared minus 6x plus 9. Remember we have this minus coefficient in front of the whole bracket, so if we expand this it's going to be minus x squared plus 6x minus 9 like this here. 6 minus 9 is equal to minus 3, so it's going to be this here, and then we're going to move all of this stuff onto this side to make a quadratic equation, so it's still going to be minus x squared. So this minus x is going to come on this side, so it's going to be a plus x, and then 6x plus x is 7x, and then this k is going to come on this side, so it's going to become minus k like this here, and this is equal to 0. We have this minus coefficient in front of the x squared, so just to simplify this and to get it into a bit of an easier format, we're going to multiply everything in this equation by minus 1, so it becomes x squared minus 7x plus 3 plus k, and this is equal to 0. So this is a quadratic equation. So what are we going to do with this? Well, we're told that this line and this curve, they intersect at two distinct points. So if we consider the discriminant, so remember the discriminant is b squared minus 4ac. We talked about the discriminant back in year 1. We did a video on it. The discriminant, when there are two distinct points, the discriminant is bigger than 0. Remember this, if there's only one point in which they intersect, it's equal to 0, and if there's no points in which they intersect, it's less than 0. In this case, there's two distinct points, so it's bigger than 0, so b squared minus 4ac is going to be bigger than 0. So a, remember, is this coefficient of x squared, b is coefficient of x, and c is this here. So if we sub these values in, it's going to be b squared, so it's going to be minus 7 squared, minus 4a, so this here is 1, and then c is this 3 plus k, and this is bigger than 0. And what's nice about this is we've created an inequality, and we can make k the subject, and therefore we can find the range of values for k. Okay, so let's rearrange this inequality in order to make k the subject. So we have minus 7 squared, which is equal to 49, minus 4 times 1, we can ignore the times 1, so minus 4 times 3 plus k. Minus 4 times 3 is minus 12, and minus 4 times k is minus 4k. Then 49 minus 12 is equal to 37. So we have 37 minus 4k is bigger than 0, and then move the minus 4k onto the other side to get the 37 is bigger than 4k, and then divide both sides by 4 to get this inequality here, that k is smaller than 37 over 4. Okay, and if you think about it, this makes sense that k has to be, so remember k is the y-intercept, it has to be smaller than a certain value, which is 37 over 4. If k, the y-intercept, was really big, so for example if it was up here, the line, you can see that this doesn't intersect the line twice. Okay, so k is smaller than 37 over 4. Now there's one more key thing with this question. Okay, now we have solved this question for the curve y is equal to 6 minus x minus 3 to the power of 2. However, one thing we haven't considered is the domain, which is between 1 and 5. So for example, let's say that we had a line that was down here, like this here. Now we can see that on our curve this only intersects the curve once. However, if we don't consider the domain, you can see that the line will keep going down like this here, and you can see that it will intersect it again. And that is essentially what we figured out here. We've essentially said that k has to be smaller than 37 over 4, but it can keep going down k. It can be as small as you want, and it will still intersect the line twice. And we can see that because of our domain, we can see that this isn't the case. There are sections where it won't intersect it twice, and this is because of this endpoint here at 5, 2. So we also need to consider this. So what we're going to do is the smallest, the lowest line that this x plus y is equal to k could be is this here, where it intersects it twice here and at this point 5, 2. Anything smaller than this and it doesn't intersect it here. Okay, so this is the lowest line that x plus y is equal to k could be. Okay, so you can see that this intersects at the point 5, 2. So what we're going to do is we're going to find what k is when it intersects x is equal to 5 and y is equal to 2. So that's what I've done here. So I've subbed in for x, I've subbed in 5, and for y I've subbed in 2, and this is equal to k, and 5 plus 2 is 7. So this here is the value of k, the y-intercept 7, the final point where it will intersect twice. So what that means is anything lower than this, it won't intersect the curve twice, and therefore k also has to be bigger than 7. It can also be equal to it, because then it will intersect this point here at 5, 2. So therefore this here is the answer. So k has to be bigger than or equal to 7, but smaller than 37 over 4. It wants the answer in set notation. We've talked about set notation before, essentially just a different way of writing it. It's like this here, where we say k where k is bigger than or equal to 7 but smaller than 37 over 4. And this here is the final answer. So I'd say this is a pretty tricky question with all of the things considered, getting both of these inequalities here. Okay, so here's one final exam question where we're told that the curve C1 with parametric equations x is equal to 10 cos t and y is equal to 4 root 2 sin t meets the circle C2 with equation x squared plus y squared is equal to 66, and we're told that they have 4 distinct points of intersection. So we can see this on this graph up here. So we have C2, which is this circle here, and we have C1. This is kind of like this oval, this like elongated circle here, which is the parametric equations, and we're told they meet 4 times here, 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 and here. And we're told that one of these points S lies in the 4th quadrant, so we can see that here. Remember, this is the first, this is the second, this is the third, and this is the 4th quadrant, so S lies in the 4th quadrant, and we need to find the coordinates of S. Now, as S is in the 4th quadrant, we can see that X is going to be positive, but Y is going to be negative, and this will be useful to us later on in this question. So we've talked about already in this video points of intersection between two curves, with one of them being a parametric, and the best way to do this is if we look at this equation here, x squared plus y squared is equal to 66. We have this parametric equation for x and this parametric equation for y. The best way to solve this is to sub in, so we have this x squared, sub in the x here, this 10 cos t, and for y, sub in this y here, this 4 root 2 sin t. So that's what I've done up here. So it's x squared, but now instead of x it's this 10 cos t, and then it's plus y squared, but now instead of y it's this 4 root 2 sin t squared, like this here, and this is all equal to 66. So we can simplify this by expanding the brackets. We have these two squared parts here. 10 squared is 100, and that's going to be cos squared t, plus, and then 4 root 2 squared is 32, and that's going to be sin squared t is equal to 66. Now this here is a trigonometric quadratic. Now we've talked about how to solve these back in chapter 6. We did a video called Trigonometric Identities and Equations, and one of the things we talked about, that when we're solving these we don't like having more than one trigonometric function. So here we have a problem because we have sin and cos, we only want one of them, and the way that we're going to eliminate one of them is use the trigonometric identity that sin squared t plus cos squared t is equivalent to 1. Let's eliminate the cos t. So what we're going to do, this sin squared t, we're going to move this to the other side to make cos squared t the subject. So it becomes cos squared t is equivalent to 1 minus sin squared t. So what we're going to do is sub out this cos squared t here for this 1 minus sin squared t. So therefore it's going to be 100, and then instead of this cos squared t here, it's now going to be this 1 minus sin squared t, like this here, and then plus the 32 sin squared t is equal to 66. We can expand this bracket here, so 100 times 1 is 100, and 100 times minus sin squared t is minus 100 sin squared t, and then we have this minus 100 sin squared t plus 32 sin squared t that will simplify to minus 68 sin squared t. Move this 100 here to the other side, so it's 66 minus 100, which is minus 34, and divide both sides here by this minus 68, so we get the sin squared t is equal to a half, and then if we square root both sides we get that sin t is equal to plus or minus 1 over root 2. Now which one is it going to be? Now if we look at sin t, so sin t appears in the parametric equation for y. Now we know y is going to be negative because s is in the 4th quadrant. So if we look at sin t, in order for y to be negative, sin t is also going to be negative. So when we look at this here, we therefore know that sin t has to be equal to the minus 1 over root 2. So therefore sin t is going to be equal to this minus 1 over root 2. I've written it as root 2 over 2 by just timesing this 1 over root 2 by root 2 over root 2 to get rid of the surd in the denominator, and it's in this more common format here. So sin t is equal to minus root 2 over 2. Okay, so we have that sin t is equal to minus root 2 over 2. So in order to find t, let's take the inverse sin of minus root 2 over 2, which if you put it into your calculator is equal to minus pi over 4. Now annoyingly this isn't in this domain here, so this isn't a possible answer for t. However, and I've talked about this approach in my previous videos on trigonometry, if we draw a sin graph like this here, so we can see that if we go to minus pi over 2 in this direction, here I've drawn a line that indicates this minus root 2 over 2, and you can see this point of intersection here at this minus pi over 4, and you can see that in this domain between 0 and 2 pi we have 2 points of intersection here. So between 0 and 2 pi there are 2 values that give this minus root 2 over 2. So how do we find them? Well, we know that this point here is minus pi over 4, and what we do is we use the knowledge that trigonometric graphs are symmetric. So what do I mean by that? So we know that the distance between here, which is when x is equal to 0, and here, which is minus pi over 4, we know that this distance here is pi over 4, obviously. So what this means is the distance here between pi and this point here is also pi over 4, and we know that the distance between this point here and this 2 pi is also pi over 4. So therefore, to find these 2 points here, t is going to be pi here plus this difference, which is pi over 4, which is equal to 5 pi over 4, and 2 pi minus this pi over 4 to get it here, and this is going to be 7 pi over 4. So therefore there are 2 t values in this domain between 0 and 2 pi that give out when you do the sign of it, you get this minus root 2 over 2, which is 5 pi over 4 and 7 pi over 4. Okay, so which t value is it that gives this s here? Okay, well let's consider this by subbing in these t values into the parametric equation for x. So that's what I've done here. So x is equal to 10 cos t, so 5 pi over 4 and 7 pi over 4. If you put both of these into your calculator, the 5 pi over 4 gives out minus 5 root 2, and the 7 pi over 4 gives out 5 root 2. We know that x is going to be positive because it's in the 4th quadrant, so that means it's not going to be this answer, it's going to be this answer here where it gives out the positive number. So therefore t is equal to 7 pi over 4. We know that x is equal to 5 root 2. So all we just need to do now is find y, and we can do it using this parametric equation here. So y is equal to 4 root 2. We already know that sin t is equal to minus root 2 over 2, like this here. So 4 root 2 multiplied by minus root 2 over 2 is equal to minus 4. So x is equal to 5 root 2, y is equal to minus 4. So therefore the coordinates of this point here, s, are 5 root 2 minus 4.